Today, I received an MPPT charger from a customer for repair. The unit is completely non-functional, and the display remains blank. Let's take a look inside this charger to see what's going on and how we can bring it back to life. This is a Chinese-made MPPT solar charge controller. It supports an input voltage of up to 180 volts and provides an output current of 45S, making it suitable for 12-volt to 48-volt battery systems. I previously used a similar unit for about a year and was quite satisfied with its performance. The only drawback was that it became fairly noisy when operating at full power. I'll take it apart and show you the main sections of this charger. This charger uses an auxiliary power supply module that converts the PV input voltage into several lower voltage rails, such as 12 volts, 15 volts, and 5 volts, to power the different circuits inside the unit. The main controller is an STM32 microcontroller. It is programmed to track the maximum power point, MPPT, and control the buck converter stage. The buck converter uses two IRFP4668 MOSFETs connected in parallel and driven by an ID7S625 gate driver IC. This IC is functionally equivalent to the IR2113, so they can be used as replacements for each other when necessary. The charger also includes an ACS7112 current sensor IC, which is used to measure the PV input current. Overall, the design of this charger is quite straightforward, and I also have the hex firmware file for the STM32 microcontroller. If you're interested in purchasing the hex file, you can contact me. The price is $50. Next comes the troubleshooting process. Since the charger has a blank display and shows no signs of operation, we'll start by checking the power supply section first. Here I'm using the diode test mode to check the MOSFETs in the auxiliary power supply module. As expected, the MOSFET is shorted. I also noticed that the MOSFET was glued directly to the aluminum heatsink. This may have resulted in poor heat transfer, causing the device to overheat and eventually fail. Next, I checked the two MOSFETs in the buck converter stage and found that both of them were shorted as well. It's possible that an unstable 12-volt supply contributed to their failure. I didn't have the exact replacement MOSFETs available, so I installed equivalent MOSFETs rated at 200 volts and 90A instead. I also replaced the thermal pads for both the MOSFETs and the diode. In the original design, the manufacturer used double-sided adhesive tape to attach the components to the aluminum heatsink. Yes, you heard that right. Double-sided tape. This is not a good solution for heat transfer and can significantly reduce cooling performance. I removed the original tape and replaced it with proper silicone thermal pads. I also applied MX6 thermal paste to improve the thermal contact between the components and the heatsink. These modifications should allow the MOSFETs and diode to dissipate heat much more effectively, helping to improve the long-term reliability of the charger. After replacing the faulty components, the charger powered up again and the display came back to life. I then tested the MPPT charger by charging a 75 Ah lithium battery bank. The charging current was set to 45 ACE, which is the maximum rated output of the charger. During the test, the charger operated normally, remaining stable and relatively cool. So in this video, we've seen how poor thermal design and questionable manufacturing choices led to the failure of this MPPT charger. Even though this is a budget product, I still expect a higher level of attention to detail during the manufacturing process. I hope this video provides some useful information and helps you troubleshoot and repair similar MPPT chargers in the future. Thanks for watching, and I'll see you in the next video.